time we considered a scheme of quantum teleportation. Let's now discuss how quantum teleportation can be realized in practice. To date, quantum teleportation has been performed over pretty long distances. In 2012, quantum teleportation was performed over 143 kilometers between Tenerife and Palm Islands in the Atlantic Ocean. And in 2017, the distance of 1,400 kilometers was achieved during the teleportation between low orbit satellite and Earth. In today's lesson, we consider a bit simplified scheme of quantum teleportation. It was suggested in 1997 by Anton Selinger's group in the very first experiment on quantum teleportation. It differs from the more modern schemes only in a measurement procedure, which is simpler here. All other stages are not so much different. The photon with two possible polarizations acts here as a qubit. You can see the experimental setup presented on the slide. As we already know, the aim is to transfer a photon's state psi from Alice to Bob. Alice and Bob are distanced from each other. They could be in different cities, for example. So, in the beginning, Alice generates a pair of entangled photons in a Bell state. The most convenient here is the singlet state beta 11. This minus inside the state will be useful to create a destructive interference. Then, she sends one of her entangled photons to Bob, while keeping the second photons, and perform a measurement analogous to a measurement in the Bell basis on the second photon and a photon in the state psi. After that, she reports the measurement results to Bob using classical channel, and Bob performs some transform on his photon if required. Then the teleportation is over and its credibility is confirmed by the pair of detectors D1 and D2. Let's consider this scheme step by step. First of all, let's learn how does Alice generate photons in the state beta 11. For this purpose, the process of spontaneous parametric Jones conversion is used. You can see it on the slide. A strong laser pumping depicted by a blue arrow brings atoms of a type 2 nonlinear crystal into an excited state. The resonance pumping frequency is far off the resonance with the excited band, and the whole process is strongly non-resonant. As a result, the excited state appears to be unstable and decays quickly, emitting a pair of photons. The photons will propagate in certain directions and have certain energies. In optics, these photons are typically referred to as ones being radiated in certain modes. Since we are dealing with the parametric Jones conversion, we also adopt the traditional notation and call the photons to be the signal and the idler ones. They are denoted by red and yellow arrows respectively. Note that the process of parametric down conversion goes with quite low efficiency, and most of the pumping photons will just propagate through the crystal. However, this efficiency is enough for Alice's purposes. In accordance with the law of conservation of energy, the sum of energies of signal and idler photons must be equal to the energy of a pumping photon. We are interested in a degenerate parametrical process, where the frequencies of signal and the idler photons are equal. The total impulse also conserves, and it is also often referred to as phase matching. According to this condition, the propagation directions of signal and idler photons are interconnected, and the sum of the corresponding wave vectors for these photons must be equal to a wave vector of the pumping photon. It turns out that all possible propagation directions of the photons can be described with a pair of cones, and the wave vectors of photons will lay on the surfaces of these two cones. The cones are depicted on the slide by yellow and red colors. As can be seen from the picture, two directions will belong to the first and the second cone. For example, if the signal photon propagates in the first direction, then the idler one will propagate in the second direction. These are two directions we are interested in. The thing is, within the spontaneous decay, the signal and Euler photons will have orthogonal polarizations with respect to each other. Moreover, these photons will be in an entangled quantum state. So, if we measure the polarization of one of them, the polarization of the second one will always be orthogonal. Let's assume for simplicity that the photons have linear polarizations. So, the quantum state is then a superposition of two terms. In the first term, the signal photon has horizontal polarization and the Euler one has vertical polarization. The second term represents a reverse situation. The signal photon has vertical polarization and the Euler one has horizontal polarization. The only thing that separates this state from the one Alice has to prepare is a phase factor, denoted by e to the I phi. In order to transform this factor to -1 and obtain the Bell state beta as 1, one has to act like in classical optics and just put the glass plate of a certain thickness to obtain a required phase shift. After that, the state beta 1 can be used for quantum teleportation. But before going back to the experiment scheme, we'll consider one simple but very illustrative physical phenomena. This is a two-photon interference effect known as the Hong-O-Mandel effect. It will help us to figure out how Alice performs her measurement process. So, two identical photons enter a beam splitter that is symmetrical and insensitive to the polarization of incident radiation. The photons have the same polarization, frequency, etc. The only things that are different are the propagation directions denoted by orange and green dashed arrows. Then there is a question. What will show the detectors installed past the beam splitter? It's obvious that the following four processes may occur with the same probability. The first one. The photon that went from the left bounces off the beam splitter and goes to the left detector, and the photon that went from the right goes through the plate without any reflection and also goes towards the left detector. The second option. Two photons go through the beam splitter without any reflections. The photon that went from the left will be received by the right detector, and the photon that went from the right will be received by the left detector. The third variant. Both photons bounce off the beam splitter. So now the left photon will be caught by the left detector and the right photon will be caught by the left detector. And finally, for the fourth option, the left photon propagates through the beam splitter and the right one goes with reflection. Both of them will be received by the right detector. Since we want to describe the process using quantum mechanics, let's match these variants with the quantum states. Let's act a bit reckless and enumerate the photons. The one that goes from the left will be denoted by 1, and the one that goes from the right by 2. So, if the beam splitter is symmetrical and we have a probability of 1/2 for it to reflect and to pass the photon in any direction, then we obtain a superposition describing all four situations, which could occur, as we assume, after the detection of these two photons. Note that the third and the fourth terms go with the minus sign. This sign appears as a result of the energy conservation law, which sets some conditions of the transmission and reflection coefficients of the beam splitter. In fact, these conditions follow from the ABCD matrix analysis and relate to classical physics. And now let's set conditions imposed by quantum mechanics. At first, we defined photons as indistinguishable. They have the same polarization, the same frequencies, and the other characteristics. The only thing that they are different in are the initial directions. So the case where two photons go through the beam splitter without reflections and the case where two photons bounce off it turns to be completely undistinguishable from the point of quantum mechanics. In other words, now we don't know which one of the photons was the first one and which one was the second one. That's why we can now erase the photons' numbers and see that the second and the third terms in the sum are equal. Some photon will be caught by the left detector and some photon will be caught by the right one. Since the beam splitter is symmetrical, these terms have the same probability amplitude, but as we have learned before, they go with different signs. These two terms remove each other, and this is referred to as destructive interference. As a result, only the first and the fourth term remain in the superposition, and the photons can only be received both by left or both by the right detector in an experiment. It's quite an obvious result, which provides us with a good illustration. In fact, it shows us that in order to build a quantum mechanical description of a certain physical system, one has to describe accurately all the possible events that may occur in the system and calculate their probabilities carefully. We won't make this calculation here for our experiment scheme. You can find it in the lesson materials. We only note that the photons at the input and the beam splitter are not just identical. Now they're in a certain superposition. In order to take the occurring interference into account correctly, one has now to take each term of the superposition into account. Let's now try to give a qualitative description of what will Alice get after the measurement of qubits. As we have learned in the last lesson, in order to realize the quantum teleportation, one has to perform measurement in a Bell basis. And we have an analogous measurement in our experiment here. And the most important thing, despite a state of qubit we teleport is unknown, one of the 4 Bell states will be realized if we measure the qubit. It's only important to distinguish these 4 states. This is what our detectors are needed for. So, if we have a singlet Bell state beta 1, 1, one detector from the left pair and one detector from the right pair will be triggered. It doesn't matter which detectors exactly will trigger. The only thing that matters is that in a singlet state, the photons go in different directions after the first beam splitter. In other Bell states, we'll have 2 photons going both right or both left, and we have only right or only left pair of detectors triggered. It's actually what has been done in the original experiment in 1997. The state psi of a qubit was transferred from Alice to Bob only if state beta 1, 1 was registered. Actually, in that experiment, only 2 detectors were used because it was needed to show that photons go in different directions after the beam splitter. In this case, Bob has to do nothing with his photon. His qubit will be in a state psi. This is analogous to the state beta 00 for the scheme considered in the last lesson. Such teleportation that occurs only within a specified condition is called conditional teleportation. The scheme presented on the slide is also conditional. However, not only the state beta 1, 1 can be registered. One can also register the state beta 0, 1, which has different sign between terms, and photons in every superposition states have different polarizations. In this case, despite photons go in the same direction after the first plate, they will split when they are going through the plate sensible to polarization, and detectors only both in the left or only both in the right pair will be registered. The only thing that Bob has to do in order to perform teleportation is to restore the correct phase relations for his qubit. The other 2 Bell states are indistinguishable in this scheme. In both cases, the photons will go in the same direction after the first plate, and then on the second polarization sensible splitter they will also go in the same direction, since they will have the same polarization and only one of the 4 detectors will be triggered. Of course, this scheme can be complicated to make these 2 cases distinguishable also, but we won't do it here. And that's all. Thank you for your attention.